seagrasses are a vital habitat to coastal ecosystems around the world. We can use GIS to map these habitats by temporal scales and spatial scales. The paper today I'm going to be talking about compares these two differences and which one is better and why it's better. But in order to talk a little bit more in detail about that, instead of being out here in the ocean, let's bring it back to the computer. So I'll see you there in a second. So welcome back to the computer now. We're going to talk a little bit more about some of the actual details of this report. So it's titled The Use of Imagery and GIS Techniques to Evaluate and Compare Seagrass Dynamics Across Multiple Spatial and Temporal Scales. It was written by two ladies, Kristen A. Kaufman and Susan S. Bell, published originally online in June of 2020, but was officially published in 2022 in the 45th volume of Estuaries and Coasts. A brief outline of the study is that it was done in Tampa Bay, Florida, at several different study sites, comparing two different spatial scales, a broad scale and a fine scale imaging system. This was done over a temporal scale as well on a biennial time gradient from 2004 to 2008. And the overall consensus was that a higher resolution images from fine scale mapping depicted a significantly less seagrass overall than the broad scale imaging did. So the introduction of this paper talked a little bit about how broad scale mapping systems already in place in Tampa Bay were crucial to understanding the overall changes in seagrass dynamics at a large scale. It actually mapped an increase in seagrass cover from 1988 to 2016 by almost double in size, from 9,000 hectares of seagrass covered area to 17,000 hectares. Fine scale mapping is more accurately able to depict temporal losses within seagrass habitats by season or just in general losses over a short period of time, but haven't been used as much for large spatial areas because of their difficulty to set up. The purpose of this study, however, was to map seagrass dynamics using a fine scale gradient or fine scale resolution across a large spatial scale using data from remote sensing. So the study side of this project was done in Tampa Bay, Florida, having 30 study sites randomly selected around the bay, with 15 of them being a small landscape window and 15 of them being a large landscape window. The sizes were as follow below. 0.07 hectares or less for a small landscape, and between 2.02 and 0.07 hectares for the large landscape. They were measured at two different spatial scales, a fine scale, like we mentioned earlier, which is a 1 to 500 ratio, using manually inserted GeoTIFF files at about a meter squared each. And the broad scale mapping was done at about a 1/24,000 ratio, with 0.3 meters equaling 1 pixel. The temporal scale was done because it was actually a retrospective study. In 2006 to 2008, they observed one of the largest losses in seagrass cover. So they wanted to bring it back to 2004 to see if that same pattern was going into 2006. Polygons from gaps and fragmentation in seagrass cover from 2008 were overlaid onto the 2004 and 2006 maps to visually follow this pattern of seagrass loss. Through the broad scale system, there are three different definitions of seagrass cover. It was unvegetated tidal flats, was any seagrass areas with less than 25% bottom cover. Patchy seagrass was defined as between 25% to 75% bottom cover of seagrass, and continuous was any areas with seagrass cover was greater than 75%. This image over here on the right depicts areas that would be defined as patchy, continuous, or unvegetated in the in the broad scale system. So certain calculations were done as well. The fine scale system, how its area of seagrass was calculated, was using an area weighted mean perimeter to area ratio, or known as AWNPAR, which was calculated using this formula over here on the right, with the ratio of perimeter to area times this area over the sum of the areas. This was used to calculate various metrics through with these polygons, including patch count, change in percent cover, net seagrass loss, and net seagrass area. So moving into the results section of this study, it was found that broad scale mapping systems found 24 sites to be patchy classification, with 6 sites being classified as an unvegetated tidal flat. Fine scale mapping actually found that all 30 of these sites had some level of vegetation. And actually, overall, fine scale mapping detected 56% less seagrass cover than broad scale mapping did. And that is because of the amount of sand in between individual patches was not picked up by the broad scale mapping, but was by the fine scale. But overall, between 2004 to 2008, there was an increase in seagrass cover, with fine scale only detecting a 29% increase and broad scale detecting a 41% increase. Table 2 over here shows the total area in meters squared of seagrass mapped annually for all 30 landscape windows. In broad scale mapping, it detected 174,000 meters squared, almost 175,000 meters squared, whereas fine scale mapping only detected about 75,000 meters squared. So there's a 100,000 meters squared difference in seagrass detection from fine scale to broad scale. Moving into what I was talking about a little bit earlier with how polygons showing from gaps in seagrass cover were overlaid onto 2004 and 2006 maps to see if we could observe any chronic loss in seagrass. And figure 3 over here on the left side of the screen shows how the broad scale mapping overlay classifies this bare area as patchy seagrass instead of being a bare open water, open tidal flat. However, over here in figure 6, further down into the paper, it actually is able to consider these areas to be unvegetated after chronic periods of loss and gaps. So this brings us into my closing thoughts for this article. In the discussion, they mentioned that over the period of the study, the broad scale mapping system documented a larger seagrass cover than the fine scale system. About a 56% less seagrass was detected in fine scale than broad scale maps. And even in the fine scale maps, temporally, only 7 areas of the 30 study sites experienced a net loss in seagrass cover. And the common causes of this were creations of gaps or fragmentation of individual patches that we can see here, with these gaps forming here, and the seagrass overall began to deteriorate, and more gaps began to appear. While I was reading this paper, though, I had this idea that what kind of issues would arise with problems and imaging with submerged vegetation, with issues with light refraction and distortion of images and overall scattering due to suspended sediments and particles in the water. This last section wasn't in the paper, but it's just some thoughts that I had about it because of my experience working with seagrass in the field. So with that, that's my closing thought. Here is the citation for use for any of you all. And the link should be posted underneath the video as well as that Word document. Thank you for watching and have a good day.